so moving right along, let's talk about the whole inactivated vaccines. And so this is going to be a non-replicating as opposed to the live attenuated, non-pathogenic, again, as opposed to the live attenuated, virus, bacteria, or some type of pathogen potentially. And again, the idea here is that in the previous example, right, I gave this pathogen to this patient essentially. I just kind of decreased its pathogenicity in some way. In this situation, I'm going to just kill this organism and then give it to the patient. That's essentially the difference. So this organism cannot replicate. It cannot infect cells. And you might be saying, okay, well, how does that differ when you start to talk about some of these different pathways in the immune response? Well, let's think of it this way, right? If I just gave this patient a killed organism, can the dendritic cell still present a killed organism's antigens on MHC2? And the answer to that question is absolutely, right? This dendritic cell can still find this killed organism that's floating around there in the blood or the lymphoid tissue, and it can go up to it and it can phagocytose it, right? And so this dendritic cell can phagocytose this pathogen, and in doing so can present it on MHC2. And so that answers kind of the first question. If I can put it on MHC2, I know that I can get CD4 positive T cells to bind to that, right? And that can cause eventually B cell activation, CD40 ligand binding, class switching, and I can generate IgG antibodies to this pathogen. So I can generate humoral IgG antibodies to that pathogen, right? And that's what we also saw with live attenuated, right? We saw we could get a humoral response there with IgG antibodies, memory response, right? From the class switching from the CD40 ligand binding. The question here is, well, I don't see cellular on this side. Why is that? Well, let's think about this for a second. So again, if I kill this organism, okay, so remember now I'm killing it, can a killed organism infect a dendritic cell? Probably not, right? If this organism's killed, it's not going to be going around infecting dendritic cells. So can I present it on MHC1 on this dendritic cell? Probably not, right? Because it's not infecting the dendritic cell. For it to get onto MHC1, it's got to infect the dendritic cell. And in doing so, when a cell is infected, when any normal nucleated cell is infected, it's going to present that antigen saying, hey, this is a virus inside of me, or this is a cancer. This is not normal. It's not a self-antigen. I need to get basically this cell is a suicide cell, or a cell that needs to self-destruct and destroy itself because that cell is infected. Now you have cytotoxic T cells that come in and destroy those cells. If this can infect a dendritic cell, it's not going to get presented on MHC1. So because of that, you're not going to get a memory cell-mediated response, which is going to decrease the efficacy / immune response that you're going to get from a killed vaccine. So that's why I put on here, you're going to get a stronger immune response in general from a live attenuated vaccine. Now, what's the upside to these killed vaccines then? Well, a big upside is you don't have to worry as much about acquisition of virulence factors causing higher pathogenicity because the organism's killed, right? We're not worrying about the organism getting stronger and causing an infection in an immunocompromised host. These organisms are killed, so it's very unlikely for that to happen. And the flu vaccine, which we're all probably somewhat familiar with at this point, and especially in the United States, you're going to see this given intramuscularly. And this is exactly what kind of vaccine this is, right? It's a killed inactivated vaccine. We're taking the influenza virus, we're killing it, and then we're giving it to the patient. And that's essentially what we're looking at. And so they should generate a humoral IgG response. However, over time, some of that IgG, if we're not exposed to it, we might lose some of that memory response over time. We might lose some of those memory cells. And so for some of these vaccines, especially as we go down, you'll see there will be boosters that are involved. You might be saying, oh, is that why I get a influenza shot every year? Not quite. The reason you get an influenza shot every year is because proteins on the virus are kind of mutating or changing. And essentially, we're trying to predict every year what those proteins might be. And that's when that's what your flu shot is for. But in general, as we start to go this way, right, particularly when we get down to this polysaccharide inactivated vaccine, we're going to start to talk about why boosters become so important, okay? And you'll see hepatitis A, also whole inactivated. And again, knowing the differences here, right? Hepatitis A is a killed vaccine, but hepatitis B in particular is going to be a subunit protein that we're going to be giving the patient, particularly that Hep B surface antigen. And then again, we talked about the polio vaccine, right? So you have the Salk and the Sabin. Remember the K at the end for killed here, and then the Sabin is the active, and then also Salmonella typhi is in this conversation as well. But essentially, that's the big difference, right? The big difference is you're not getting a cellular response because the virus is killed. It's not infecting the dendritic cells to then have it be presented on MHC1. So that's the concept.